go to, okay. All right, so this is always frustrating. There we go. All right. So what we started talking about the other day was the Laplace transform. We're not going to say a whole lot about the Laplace transform other than it's the Laplace transform. What was the idea of the Laplace transform? What do we use it for? What is it?
Solve circuits with different types of inputs.
Solve circuits with different types of inputs. In other words, so we basically, DC circuits were DC circuits. You solve that with whatever input you want, right? You could have a triangle wave going into a DC circuit. That's fine, right? When I say DC circuit with just resistors, right? That's a very easy circuit to deal with. Once we get into circuits where we have sinusoidal sources and capacitors and inductors, it's a tougher thing. We learned the phasor idea, right? Phasors only apply in what specific case? What do I have to have?
Sinusoidal.
Yep, sinusoidal waves, right? Laplace applies with anything, although we're still going to largely apply it with sine waves, all right? And there's reasons for that, because a lot of the waveforms that we talk about can be thought of as sums of sine waves in different ways. And we're going to see why we do that a little bit today. And I'm going to focus in on this thing called the concept of filtering, which I talked about a little bit the other day. So, all right, let's take a look at this circuit here. So I got V of t, I've got a resistor, a capacitor, and an inductor. And I want to figure out, the other day I introduced this idea of a transfer function, right? And in the idea of the transfer function, I say, well, what I can do is I can look at the circuit and use this idea of the Laplace impedance, right? To be able to go from a transform of my input to a transform of my output, okay? And the input is always some source, some voltage source or some current source. And the output is some current or voltage in the circuit somewhere, okay? So in this circuit, I could figure out V sub c of t by writing differential equation. Like we all agree we don't want to do that, right? So we talked a little bit the other day and I said, all right, if I look at a capacitor, all right, capacitor and inductor, so V sub c and I sub c. The relationship that exists for those guys in the time domain is what? I sub c equals what? C dV c dt. That's our time domain relationship. The idea with the Laplace transform, right, is we said, all right, if I take the Laplace transform of this expression, so I Laplace transform both sides of that guy, what happens to the two time variables, IC and VC? What happens to them? What do I? IS and VM. Yeah, so they become IC of S and VC of S. So I replace them. Now I also have this d by dt. What do we say we do when we have a derivative? Replace it by S. So I get C times S. So we usually write that as SC times V sub C of S. And that looks Ohm's law-ish, doesn't it? Right? Well, Ohm's law isn't usually I equals something times V. It's usually V equals something times I, right? So what we said is this guy has an impedance that is what?
1 over SC.
1 over SC. Yeah, 1 over SC. Now we're going to relate that to the j omega thing here in a little bit. Okay. So I want to figure out the Laplace impedance thing of this guy. So needless to say, we talked about last time also for the inductor. What was our relationship between IL and VL here? What was that relationship? Well, we know that VL equals LdIL by dt, right? VL equals LdIL by dt. So VL of S, when I transform that, is equal to what? Yep. Yeah, usually SL is how we write it. SL times IL of S. So what's our impedance in that case? S times L. Yeah, right? All right, so resistor, uninteresting, it's R, right? There's nothing really to derive about that. All right, so let's say I wanted to solve for V sub c of t. Well, what I would have to do is I would have to transform this guy over into the Laplace domain, right? I would say, all right, transform this guy over. All right, and it becomes, let me do it up here. This out of the way. All right. Instead of v of t, I say I have v of s. I have r. I have c. What do I replace c with here?
1 over SC.
Yeah, 1 over sc. Yeah, and then I have sl for this guy. Okay, like that. And I want to solve for the capacitor voltage, I called it, although technically it's also the inductor voltage. I'm just going to call it v sub c of s. So what I want to get is what I called a transfer function the other day. I want to get something that says how the transfer function describes how I transfer from an input to an output, right? So it's written like this: v sub c of s equals h of s times v of s. I want to figure out how the function, the transfer function that I would multiply the transform of vs by to figure out the transform of vc. And then if I wanted to, I can inverse Laplace transform that to figure out the time domain expression. Okay. Now, we're not going to do a lot of inverse Laplace transforming. You have one on problem 2 of the homework, probably the only one you're going to have. Okay. Maybe you'd have it on a test, probably not. Right? I don't think you'll see that on a test.
Quick question.
Sorry about that one.
I don't think you'll see it on a test. What was that?
What's h of s again?
H of s is what I call this transfer function thing. All right. And our goal right now is going to be to figure out for this circuit, what is that transfer function?
Okay, thank you.
All right, transfer function. All right, so how do I do that here? How do I figure that out? Simplify the circuit, right? I just got to do some circuit analysis. So forget about the word transfer function, right? What you have is a voltage source, resistor, capacitor, and inductor. And I say to you, tell me the voltage across the capacitor. This is nothing different than what you've done in the past. What kind of circuit is that?
Voltage divider.
Voltage divider, all right? And what are the things in the voltage divider here? So voltage divider, we have 2 elements in series. What are the 2 elements that are in series here?
The
Resistor and capacitor.
Capacitor.
The resistor and the combination of the capacitor and the inductor, right? So in other words, this guy is, if I want to think of it this way, if I simplify it, here's V of S. Here's R. And here is a little block that's going to be ZL in parallel with ZC. Like that. That's a voltage divider now. Okay? So I want to find the transfer function. Basically, it's going to be the voltage divider relationship that helps me get from VC or from V of S to VC of S. So I have, here's V, here's R, and here's 1 over SC in parallel with SL. Okay, like so.
But the voltage flowing through that combination.
Voltage never flows.
Well,
Voltage is the pressure that forces things to flow, right? There's water pressure in your house that causes a flow of water, right? Voltage is the pressure that causes it to flow. The more pressure, the more flow I get against the resistance.
well, the pressure flowing through that inductor.
Pressure is across something. Okay, I know, and this is important. Voltage is across. Flow is through. All right. So the reason I'm pointing this out is to say, okay, well, there's a voltage across that inductor, and there's a voltage across that capacitor. That voltage is the same.
But if you combine them, is it still the same?
Sure. That's the whole. You're asking a great question, which is, I suspect, a question that a lot of you have and just haven't asked, right? If I simplify a circuit that has 2 things in parallel, then the 2 things in parallel still have the same voltage across them.
Okay.
Right? And what I'm solving for is basically, what I'm saying is, I'm sort of doing a Thevenin equivalent. I'm saying, okay, make a Thevenin equivalent for this box here. Right?
So if I were just to do the voltage divider across the capacitor.
You can't do that. Why can't, because I need to have a voltage divider, I have to have two elements in series, and the capacitor is not in series with the resistor.
Okay.
It's in parallel with the inductor, and that combination is in series with the resistor, right? So that's an important thing to note about that. All right, so here, how would I do this? Well, first thing I got to do, probably what I would say is I want to figure out that parallel impedance of those two things. So Z, I don't know, I'll call that ZEQ. Yeah, okay, we'll call it Z1 because that's what Eli likes, Z1. All right, I was thinking Z1. Now, how would you do? I know in my head that this becomes 1 over SC times SL, 1 over SC plus SL. If I have two things in parallel, that's what the parallel impedance formula becomes. All right. If you didn't know that, it's 1 over the sums, right? Right. I can do it either way, but I'll do it this way for now. One thing I said the other day is we like to get these things so that they are rational functions of S. What's a rational function? It's a fraction, and there's polynomial S on the top and a polynomial of S on the bottom. All right, do I have?
Multiply ZC.
Yeah, multiply top and bottom by SC here, right? If I do that, right, multiply top and bottom by SC, this guy goes away. And this term here becomes 1. This whole thing becomes SL over 1 plus S squared LC. Okay. And L and C and R are all numbers here. So if I was doing this in MATLAB, what I would do is I would write a little MATLAB script that has all that stuff written out. And we'll do that later in class.
Why did you want it in rational and not just solid? Like in the top?
We'll see why that is later on today. It's really hard for us to start using this stuff to make the plots and things we want to make. If it's like what I have there, run over SC times SL. It's really hard to enter that in and try to graph that thing. Okay. All right. So basically now I want to say, well, V sub C of S is what? V sub C of S, how to do the voltage divider?
Current time.
VS times.
Yep. V of S times basically that whole, yeah, that combination of stuff, right? So it's the total current, so V divided by the total impedance, so that's R plus this ugly guy here, SL 1 plus S squared LC. And then on top, I got SL over 1 plus S squared LC.
So that term would be the transfer function then.
That term is the transfer function, but again, that guy's not rational. I usually want to simplify it to a rational thing. So what would I do here to simplify this?
Multiply the top and bottom by 1 plus S squared.
Multiply by the conjugate.
Yeah, multiply this top and bottom by 1 plus S squared LC, right? This guy becomes, I'm going to do it this way. I'm going to say V sub C of S, and I'm going to bring the V of S over. So I divide both sides by V of S. That's equal to H of S. Okay, that's going to become SL times S squared LCR plus R plus SL. All right, what I did there was I multiplied top and bottom of this thing. I'm not gonna be able to fit this, right? I multiplied top and bottom by 1 plus S squared LC, right? And that's how I turn that into that rational function. In the homework problems, 3, 4, 5, right? Or 3 and 4 especially, right? You're going to have functions like what I have on the top, and you're going to want to get it to a form like the one I have in the middle. Okay. All right. That is my transfer function. That tells me basically if I knew the transform of the input, how I would figure out the transform of the output. So I'm using this term input, output. Input is some source, output is some voltage or current that I want to get. And in the problems I gave you in the homework, there might be multiple transfer functions that you end up needing to solve for, right? Sometimes the transfer functions that you need to solve for are, maybe I'll say, well, tell me what the current is, right? Or tell me what the voltage across the resistor is, right? So there's multiple different things, multiple different outputs I could potentially be interested in. Outputs are just voltages or currents in the circuit. Okay. So to do these problems, basically we can do whatever kind of circuit analysis we need to do. And often we want things to be a function of S. And there's a reason for that, which we'll see more of, because I want to look at these things as functions of frequency. I want to say at a particular frequency, what is the value of H? All right. And so one of the things, one of the reasons why we like to look so much at, I ask you about current dividers, voltage dividers, circuit simplification, is it gets really hard to do mesh and nodal when you have things symbolic, right? And very often in electronics circuits, you don't have a whole lot of mesh and nodal, all right? So,
Dr. Cox,
yeah.
You're talking about testing at different frequencies. The whole reason of using the Laplace transform is so we can test for a bunch of different inputs, right? Like we could have exponential input as well.
Yes. Well,
but exponential input doesn't have frequency. So how would that apply?
So it's a great question, Musa. The whole idea of Laplace transform is it can take any input. That's right. It can take sine waves as one type of input as well. All right. So we said last time, the two advantages of this guy is it can deal with any input, and unlike phasors, it can also deal with the transient conditions. We're going to not do the transient conditions anyway, and we're going to primarily deal with still sinusoidal inputs. There's a reason I wanted to do this, which I'll talk about here a little bit as we go through today. All right. And then we'll see if you still have that question.
Sounds good.
All right. So the whole idea is I can take different things that would have otherwise required differential equations. So basically we said differential equations is the right way to do everything. Bottom line truth, right? If I want to figure out what's going on in a circuit lives in the time domain with all of us. And so we got to do differential equations. It's annoying. So we moved to phasors. In the special case of sine waves, we can also move to Laplace transforms. In Laplace transforms, it became algebra, right? That's the beauty of it, is I take the transform of the input, multiply it by the transfer function, get the transform of the output, and then I can inverse transform to get the time domain stuff. I'm not going to worry about that whole process so much. We're going to do a lot of this type of analysis here. Now, if I look at a transfer function like this guy, right? So I did the other day, I said if I had a circuit, and we're going to look at that circuit a lot, my favorite circuit, the RC, all right? The whole world is an RC circuit. If I solve for V sub C of S, all right, what I would find, and we're going to do this again in a little bit, V sub C of S, let's screw it. Let's just do it here, right? Let's say we had this circuit, just so we can remind ourselves, and say I want to solve for V sub C of S. And I'm going to say, well, V of T has some V of S, right? What would I replace? Let me do it the right way. V sub C of T. So I move this guy to the Laplace world, right? So via the Laplace transform, I go to the Laplace world. What do I replace the capacitor with?
With 1 over S.
Yes.
1 over S.
1 over S times C.
Yeah, 1 over SC. Okay, 1 over SC. And I'm interested in V sub C of S. Okay, so what does that become?
Voltage divided.
Voltage divider again. And so I would have 1 over SC over 1 over SC plus R. We did this Monday. That guy is going to become 1 over SRC plus 1 times the voltage. Times the voltage. Like that. So I got this guy here. All right, this is my H of S, my transfer function. Okay. So if I have that transfer function, okay, what we often do, and you guys aren't going to have to do this per se, all right, but what can be done is that S is typically is used to be a complex variable, meaning it's got a real part and an imaginary part. Okay. Now, I'm not going to say a whole lot more about that, but if I took the magnitude of h of s, if I took this guy right here and I tried to plot its magnitude, right? That thing is a three-dimensional function in space, right? There's a real part to s and there's an imaginary part to s, okay? And if I plotted the magnitude at all of those values, what I would get is this guy right here. I'd get a surface, right? Like that. And it looks like that surface is getting really big at a particular point, right? Now, if I gave you this function, h of s equals SR 1 over SRC plus 1, at what value of s would the magnitude of that thing become really, really, really big?
Infinity? No, not infinity.
At what point would it become infinite? Yeah. At some point, that guy's going to become infinite, h of s. At what value of s would h of s, this particular h of s, become infinite?
Whatever makes the denominator zero.
Whatever makes the denominator equal to 0. So what value of s makes that denominator equal to 0? So I just say, well, SRC plus 1 equals 0. So I would have where s equals -1 over RC, right? And wherever that is, so if I have a value for the resistor and the capacitor, what I would say is this thing has what we call a pole at that point, all right? Now, why do we call it a pole? Because it would look like this, right? So what you see here is here's the imaginary part of S, here's the real part of S, okay? And then the magnitude is plotted on the z-axis here. So what you see is that this is the point here that is the pole. So what it kind of looks like is that this function has like a pole and somebody dropped like a little tent on top of that pole, right? That's where the terminology of a pole comes from, all right? Now, we use this term all the time in engineering, poles and zeros. So what's a zero? Well, 0 is any value of s that causes the thing to become equal to 0. So does this transfer function here have any zeros? No, it has one pole, all right, and no zeros. Problem 5 on the homework asks you to do that. There's really not a whole lot of work to do for it. You got to find where are the roots of the denominator and where are the roots of the numerator. So where is the pole? The pole is at s equal -1 over RC. So I'm going to put that right here. I don't have numbers for it, but I put that right there. So it's negative. So I know it goes in the negative. Why I put that on the? Well, I'm a bad person here. This is the imaginary part of s, and this is the real part of s. You get fired for that. Okay, you guys can fail me today. All right, so why did I put this guy on the negative real axis? So I put an X where the pole occurs, right? If I drew the three-dimensional plot, this is where this guy would be sticking off to infinity, where I drew that X, right? That's where that pole is. Why is it on the negative real axis?
Because the real part is negative.
Yeah, the real part is negative. -1 over RC, is that ever going to be a negative? Is that ever going to be an imaginary number?
So the imaginary part's always going to be 0.
It doesn't have to be, but very often it is. All right, for something like that, negative, if it's 1 over RC, there's no such thing as an imaginary resistor. All right, maybe there is an imaginary resistor, but there's no physical imaginary resistor, right? Okay, so let's say I gave you a problem like this. I said, all right, I've got 3s over s plus 2 times s plus 4 like this. All right, and I did it twice, didn't I? Somebody copied and pasted, didn't they? Imaginary of s, real of s. Okay. Where are the poles here?
Negative.
-2 and -4.
-2 and -4, right? So I got poles, at s equal to -2 and s equal to -4. So what I do is I say, all right, I got a pole here at -2 and a pole here at -4. Okay. Looks like I also have a 0 too, don't I?
Yeah, it's
The
0.
numerator.
Yeah, I got a 0 at s equal to 0. So what I do to show those is I draw a little O right there.
Isn't that like kind of redundant?
Isn't what redundant?
A 0 is 0. Like isn't.
Well, I mean,
That's not always.
it's not always going to be the case. It's not always going to be the case. So what we're going to find is that different circuits have these poles and zeros. And what we're going to find is that when I have poles, I get things that become what I call low pass in nature. All right. And so we're going to talk about that meaning here in a second. What a pole and a zero is basically what are the points where that function goes to infinity or where that function goes to 0. All right. And we use that term a lot. So beginning Friday, we're going to be talking all about poles and zeros. But in terms of identifying poles and zeros, there they are, right? It's relatively easy to identify them. They're the roots of these functions. Now,
So is a pole like an energy spike or like?
a pole is just, it's just to say that is the point at which that function goes to infinity. And it has a special meaning to us in terms of the way this particular, the way the circuit that this transfer function came from behaves a special way at the frequency that is equal to that pole frequency. All right. Again, you're like, what is he talking about? All right, we're gonna see a little bit more as we keep going through this, right? But there's nothing special about the pole other than to say I've got a mathematical function here, and a pole by definition is where that mathematical function is infinite. Right? That's all it really is. Okay, now it does have some special meaning, and so it's a good question. All right, but we'll keep going. All right, so basically what we have is this. Circuits with R's, L's, and C's, I get a transfer function that is basically this. It is always going to be, this is what I keep calling a rational function. Rational function. Meaning that there is some polynomial of S on the top and the bottom. Okay. And if I want to use this approach, basically what I need to do is I got to use partial fractions and inverse Laplace transform, and that'll get me the time domain stuff. All right. Our key thing for us is really going to be to figure out how we look at a circuit and do what we did right here. Now, what I want to switch gears to is how do I use it? All right. And in particular, I'm going to focus still on the special case of sine waves. I said sine waves are super important, right? Because if you think about pretty much anything you could do with a circuit, what could you do? So you got, if you're a power engineer, you're working with a grid. The grid has sine waves, right? All the currents and voltages are sine waves. You're an audio engineer. Audio is sine waves, right? If you do electromagnetics, radios, cell phones, any of that stuff, it's all sine waves, okay? So sine waves have a really special place in everything that we do, and so we spend a lot of time on them for that reason. If I look at this circuit right here, all right, so we went through, we got this transfer function. This h of s relates to me v sub c over v. All right, so oftentimes we'll say the transfer function is output over input, because remember, we can write this as output equals transfer function times input, right? So I will say h equals output over input, or I'll write it that way. Okay, so there's two ways of writing it. Now, let's say we had this problem right here. And so we derived for ourselves that, do I have, no, I don't. I want to get rid of this. All right, I have v sub c of s is equal to that, okay? If you want to look at that analysis is done in the last class too. So it's all in the notes there. Let's say I did want to figure out v sub c of t. I wanted to go all the way through that part, right? And I was told that the input was v cosine omega t. So if you were in differential equations, what would be my next step? And I said to you, I want to find v sub c of t. All right, so we figured out v sub c of s equals 1 over src plus 1. That's all Laplace transform stuff, all right? What would I do next in differential equations class?
Would it be to write a second order?
I wanna say find the homogeneous in particular.
Well, so when you solve differential equations, you guys all whined when we did
Inverse
different.
Laplace?
He's like, yeah, I want to do it with Laplace transforms. Everybody says. So what do I do with this? The Laplace
Inverse Laplace?
inverse Laplace, right? I got to do inverse Laplace. But first thing I got to do is I got to get the Laplace transform my input here, which is V of t. Anybody remember? The internet's got the answer, right? But what is the Laplace transform of V of t?
1 over x, or no, just.
B over s squared plus b squared.
Okay, so yeah, it's going to be s over s squared plus omega squared, where omega is, and there's a v on top, yes, because there's a amplitude. Yes. All right. Now, you may or may not remember that. All right, it's nothing special about remembering that per se. If you wanted to solve this, then you would go into basically, I had my V out of S. Oh boy, I changed it to, so V sub C, oh boy. Let's call this V out. And let's call this V in. So this can be V out of S. And this can be V in of S. All right. So what I did there was I basically wrote that same thing down, and I'm not going to go through this derivation. I've got this derivation posted on Canvas if you really want to see it, okay? But I wanted to just kind of work through the result of it here. I don't want to derive stuff per se. I took that result. This is the result from the previous slide, right? What I came down to, what's the difference between here and here? What did I do between those two steps?
Made it irrational?
No. What did I do between
You
that top?
you factored the s squared plus omega squared?
I did, yeah. S squared plus omega squared became s plus j omega times s minus j omega. Multiply those guys out and I get s squared plus.
So that makes it easier to do partial fractions
It
later.
does, thank you, yes, right? That means that this guy would turn into, essentially, if I did this right, this guy would basically be this, right? That's how you would solve this by partial fractions. K1 over S plus 1 over RC plus K2 over S minus J omega plus K3 over S plus J omega. Now I did something here because I already knew the answer. What does it mean when I write K2 with a little star over it? What's that little
Conjugate.
Star? Conjugate. What I know is going to happen, because I've done this, and again, the derivation is there in Canvas if you really want to see it. K2 and K2 conjugate are going to be conjugates, right? I know that the constants over top of those two guys would be conjugates. Now, assuming that that's correct, right? If you had this partial fraction result, tell me what the time domain version of that, inverse Laplace that for me. This would be V out of t. What would that, so yeah, K1 over S plus 1 over RC. If I have 1 over S plus a constant, what does that become once I take that to the time domain?
It's exponential.
Exponential, yeah, and it's a decaying exponential at that. So K1 e to the negative t over RC. What is that? That's the transient response. Okay, for this circuit, this would be the transient response. Now, what do I get for the other two? They're going to be exponentials. All right. K2 over S minus J omega. What does that become?
K2 e to the negative t over s minus j omega.
K2 times e to the j omega t. Right? Because if I have 1 over S plus a, it goes to e to the negative at. Like that. So if I have a negative, then it goes to a positive. Okay. And then K2 conjugate e to the negative j omega t. Now,
Isn't that just 2 cosine omega t?
All right, winner. All right, so he knew where I was going with that. So if I redo that, Yahoo would be proud, right? So you look at that, what do you have? This guy would basically become a cosine expression. If I have e to the j omega t, e to the minus j omega t, it becomes a cosine expression. Now without going through the work of all of this, all right? If you go through the work, and I've got it there in the notes for the people that really want to see it, right? Is this constant K2, if I solved out for it, would be basically, so we said we had h of s. So let's just remember h of s was 1 over s RC plus 1. Okay. What I find basically is that if I go through this analysis, this coefficient right here becomes a complex number with a magnitude that is the same as the magnitude of h of s evaluated at s equal to j omega. And then this guy is the magnitude of this guy when s equals j omega. If I carry all that result through, basically what I get is what? I basically am going to get, if I then put these two together and I used all my Yahoo 2254 knowledge, right? I would get that this is e to the negative 2 over RC, t over RC, plus v over 2 times magnitude of h of j omega times e to the j omega t plus the angle of h of j omega plus v over 2 magnitude of h of j omega.
That's just a little bit crazy. A lot.
Well, are you glad we don't do, one of the things I said, we don't do this math a lot, ever, actually. And you're glad, probably.
Mm-hmm.
Right? If I did that, what we're going to do is we're going to use the result, right? If I have those two things together, it's exactly what Musa said, right? If I look at that expression, this should make some sense. If I carry that down here, right? V over 2 times that whole thing, shouldn't that become V times the magnitude of h of j omega times what? How do I deal with that e to the j omega t plus angle h of j omega? What is that? When I simplify that whole thing, right? This is a Yahoo thing. If I have a e to the j theta plus a e to the minus j theta, what does that become? This guy becomes, 2 cosine theta, right? When I put those together. That's what this is, where theta here is omega t plus that angle, okay? I don't like focusing on this too much. I think it's important to talk about this because this is where it comes from. But we're just going to use the result pretty much, all right? So what I have is V out is this thing. Right there, right? So where's the steady state and where's the transient part?
Steady state is the second part.
Steady state's the second part. What it says is if I look only at the output, right? And this is actually really where we're sort of summarizing here. If I'm talking about sine waves, right? The steady state output is always the amplitude of the input times the magnitude of the transfer function evaluated at the frequency that I'm putting in. And then the angle of the output is the angle of the input plus the angle of the transfer function. As it turns out, you already knew that. This is just a more math way of looking at it. You did this already when you did phasor analysis, right? You basically took the phasor of the input and you related the phasor of the input to the phasor of the output, and they were related through the transfer function. This is just a different way of looking at it. This is mathy, so let's go to some examples. All right, let's try to think about what this means.
What was Vs again, when we transferred that V cosine omega t to the Laplace transform? What was that Laplace transform?
Well, V of S was the Laplace transform of the sine wave. So V times S over S squared plus omega squared, right? And you won't need to know ever again, maybe in your life, what the Laplace transform of a sine wave is or cosine wave. Right? If you're really interested and you want to see how the derivation works out, I've got it. Like I said, I got it posted so you can look at it, but I don't want to derive it. It's not that useful. Right? What it says is in general, let's say I have a circuit, okay? It could be my RC circuit, okay, that I made, that its input is cosine 10t, okay? Well, my result says that the output that I'm looking for is always, so I'm using this term, X is input, Y is output. That's a very common thing to do. X is in, Y is out, all right? Looking at this picture here, what it says is the time domain version of the output is going to be the amplitude of the input times the magnitude of the transfer function at the frequency that I'm looking at. So, okay, if I have x of t equals cosine 10t, what is the frequency that I'm looking at? What is the frequency that I'm looking at? Cosine 10t.
Cosine 10 is the angular frequency.
Well, yeah, sure. What's its angular frequency?
So we just divide 10 by 2 pi.
It's 10. All right. Its angular frequency is that.
I was thinking. Like
Okay. Yeah. It's
frequency, not
okay. Yeah. So that will be 10 over 2 pi. Yeah. Right. That's true. So the angular frequency of that guy is omega, right? What you do is say, okay, well, if this, so what I would do is I would look at h of j omega, right? So I would take that h of s, okay, and I would say plug in s equal to j omega. So plug in j10. And at j10, what we see is this thing has a magnitude that is 1 over square root of 2 and an angle that's negative 45. I'm just taking this as an example, right? If I had that particular circuit, whatever that circuit is, and it had that particular magnitude at 10 and that particular angle at 10, what would the output be? What would our y be if I had this magnitude and this angle? So
Is it
what's
1 over square root 2a cosine omega t plus phi minus 45 degrees?
Yeah, and so if you look at this particular input here, x of t, there is no a. A is equal to 1, right? Times 1. Cosine 10t, so it becomes, it's got the same frequency as going in. This guy doesn't have any phase shift, so there's no phi, all right? But there is an angle, which is negative 45 degrees. So 10t minus 45 degrees.
So is x of t our input?
X of t is our input.
Okay.
And y of t is our output. So this is our way of thinking about it. If x of t basically is a sine or a cosine like this, right? It is basically exponentials. And so what we found is if we know the frequency of the input and we know the phase of the input and the amplitude of the input, then all I got to do is take the amplitude of the input, multiply it by the transfer function magnitude, and that tells me the amplitude of the output, and I add their phases. Okay, so if I look at what I'm going to get out of this thing, is it bigger or smaller than what I put in? Smaller. Yeah, what I'm going to get is something that's smaller. Its amplitude is basically 0.707, right? So 1 over square root of 2 is 0.707 if I did the math on that. And he's shifted negative 45 degrees, which means he's going to peak a little bit later in time. He's going to be shifted over to the right.
Correct me if I'm wrong, but like last lecture you said something about that the output can never be bigger than the input, or is that, did I just make that up in my head?
If I have R's, L's, and C's, that usually doesn't happen. I can't say never. I got to be careful. Ask me about that later.
Okay.
Yeah.
Wait, so was phi 0 because there was no
Phi
input?
is 0 in this example. Yeah. So
Okay.
just to be clear, so my input x of t is cosine 10t. So for
Because
this,
there's no angle there, that's
yeah.
why
So,
that's phi.
right. So for this input, I've got a equal to 1 and phi equal to 0.
Got it.
All right.
Is there any particular, I noticed this when I was doing the homework, is there any particular reason that angle for the transfer function is always negative?
Yes. It's not always negative, but often it's negative because when the world was created, it was created to be low pass, and low pass world is always going to be negative. We'll see. You're going to see this more as we have angle.
What is low pass world?
Well, we're going to see that a little bit more. Yeah. All right. All right. Is basically the phase shifts are usually going to be negative.
So this expression for the steady state will work for any circuit with
Yep.
sinusoidal inputs?
It works for any circuit with sinusoidal inputs. That's right. Yeah, and so we use that a lot. Okay, so basically, this idea here is that the transfer function is a function. It's a function of S, right? Is a function, I'll say specifically of S, where S, if I have sine waves, S equals j omega. All right, so it basically says if I put a waveform into a circuit, the amplitudes of the currents and voltages change as the frequency of the input changes. Just kind of something that we already know, right? So let's say we had, again, my favorite circuit, the RC circuit. I get this guy, right? And we get that relationship, 1 over SRC plus 1. All right, so let's carry that guy over here. So V in, V out equals 1 over SRC plus 1 times V in of S. Okay. Now, what I said there is, all right, if I was dealing with sine waves, okay, then this guy becomes effectively a situation where what I have is S equals j omega, and I have V out equals 1 over j omega RC plus 1 times V in. Like that. Now, what happens if V in was a sine wave? Okay, and let's look at a couple of different choices. So let's say I have V in is a DC value. Okay, what do we say was the frequency of a DC value?
0.
0, right? So if I plug in omega equal to 0, what does that tell me here?
That V out is equal to V in.
V out equals V in. Now, we have a couple of ways of saying that, right? When you learned in DC circuits, you said, well, in steady state, capacitors become opens, inductors become shorts, right? So if I look at this, what's true about the impedance of a capacitor at DC at 0? What's its impedance?
Goes to infinity.
It's infinite, right? So that tells me that there's no current flow happening in the circuit, right? So there's no current flow happening in the circuit. How much voltage drop is there across the R? 0. V equals IR. No I, no V. So V in and V out are equal to each other. So what this says is if I have a DC input, the input and the output are what? They're equal. All right. So what I say is I am passing that input to the output. I just pass it right through. If I present a certain input, it just goes straight through to the output. Now let's say I took a cosine and omega was really high. Okay, so I have V out equals 1 over j omega RC plus 1, like that, times V in, like that. What happens if omega is really high? Let's say omega goes to infinity.
VR go to 0.
Well, so what happens to the impedance of the capacitor? So if I look at, first of all, let's not even think about the capacitor. Let's look at that function, right? If omega went to 0, or sorry, if omega went to infinity in this transfer function, I would have 1 over what if omega was infinite?
Really small number or really big number?
Well, 1 over a really big number, which is a very small number, right? So I have basically V out equals 0 times V in. Okay.
So V out approaches 0.
V out approaches 0. So, and that kind of makes sense because if I have a capacitor which has 1 over j omega C as its impedance, if omega is a high number, what's true about that capacitor? It's a short circuit. So there's going to be no voltage there. Okay. So what this tells me is if I what I often do, all right, and I'm going to look at a specific circuit, right? A specific circuit that has C equals 1 microfarad and R equals 1.59 kilo ohms. What I would find in this circuit is that RC equals, I wrote it down, what is it? It's 629, I think. 628.9. 628.9. All right. And so that means this guy has a pole at a particular point. His pole is going to be at negative RC, all right, equal to negative 628.9. Right, that's where his pole is located, 1 over that, right? That's over here. Now, the thing that's important about that is what we do is we often make a plot that shows us the magnitude of that thing as frequency changes. All right. So what I've done here is I've taken this h of j omega, right? So h of j omega is a function of omega. Okay. What I do is I plotted the magnitude of that. So what did I do between here and here?
Just calculated the magnitude?
Yeah, I just calculated the magnitude, right? So I have an imaginary part on the bottom and a real part on the bottom, and I basically took the magnitude of that whole thing. And what I did was I made a plot of it, right? So on the x-axis, my independent variable is omega, and I plotted the magnitude on the y-axis. So what I see is with this, right, when I had 5 volts as my input, what I do is I go to this point right here. 5 volts is at DC. So I go to DC. So here's DC, right? And I say the magnitude of this thing is 1 at that frequency. So the output is the magnitude of the transfer function at that point times the input gives me the output. Then I said, well, what happens if I put in this guy here? So 5 cosine 629t. So what do? Well, I go to 629, right? When omega is equal to 629, so this does, when it says x like that, it means that's the omega variable. That's the x-axis variable, right? Mm-hmm. So at omega equal to 629, this guy has a magnitude of 0.707. So that tells me that the amplitude of the output is 0.7071 times 5, right? So is the output going to be smaller than the input at that frequency? Yes. All right. The important thing when I look at this particular behavior that I have right here, right? I'm looking at the magnitude of h as a function of omega. Okay. If I look at that magnitude of h as a function of omega, I call this thing a low pass filter. All right. That's the term that we use for it.
Is that because lower frequencies don't get affected as much as higher frequencies?
Lower frequencies close to DC move from the input to the output, right? So if I had a frequency at DC, or an input at DC, at DC, the input and the output are equal to each other. When I had something a little higher up, in this particular case at 629 radians per second, what I got out was about 70% of what I put in, right? That's what that magnitude being 0.707 means, is I got an output that is basically 70% of what I put in. So if I was looking at this on an oscilloscope, I would get a picture like what I showed before here, right? So I'm getting, my input is one size and my output is 70% of that. He's also shifted a little bit, but the key thing I'm focusing on right now is he's going to get smaller.
So
right?
low pass filter is basically when your output is less than your input.
No, low pass filter is a circuit that passes quote unquote low frequencies. So in other
Is
words,
there
if I
any
look
way? Oh, sorry.
well, yeah. So when I look at frequencies that are low, close to DC, the magnitude of this thing is close to 1. But as I get to higher frequencies, it approaches 0. And so if at a high enough frequency, I'm going to get a very small version of the input at the output.
Doesn't that all depend on your values of RC?
all
Like what
depends on
is
your
high
value,
enough
yes.
to pass and what is low enough to
It is.
not?
Yes, that is entirely correct. It all depends on your values of R's and C's. And so when I'm an engineer and I'm a designer, what I typically am worried about is how do I choose the R and C so that it passes the things I want and gets rid of the things I don't want. Okay. So we're not going to be so much worried about design per se here. You guys are going to have circuits and you're going to need to make these plots and identify whether this guy's low pass or high pass. Now, in sort of the, we use the term, because this guy passes low frequencies, we use the term low pass filters. At higher frequencies, what we say is that the signals are quote unquote attenuated or reduced, right? So when we reduce them, when we make them smaller, we say that they're attenuated, all right? And we have kind of a basic, I don't know, dictionary, if you will, of filters that we deal with, okay? Most of the time, we deal with the first of these, the low pass filter, the high pass filter. So what I did here is, and this is kind of the general way that we define these things, right? Low pass, band pass, and high pass, right? And so we've given the standard definition. What I'm looking at on the y-axis here is the magnitude of h of j omega, okay? The magnitude of it. And I define this thing here, omega c, which is oftentimes called the cutoff frequency. We have all kinds of terms for it. But for now, I'm just going to call it the cutoff frequency, okay? Cutoff because if you look at this guy, in my ideal low-pass filter, what frequencies does this guy pass? Well, he passes everything from DC to omega C. And then what am I saying out here, ideally, for the magnitude of this filter past that point? Well, so omega is my frequency here on the y-axis or the x-axis, so it's 0, right? So at a high frequency, the magnitude of the output is 0, right? The idea here, what we're trying to convey with these pictures is to say, what frequencies do I have a magnitude that's 1, and what frequencies do I have a magnitude that's 0? Because the whole idea is I multiply the magnitude of the transfer function at a particular frequency by the magnitude of the input at that frequency. Okay.
So how the magnitude changes is what tells you what filter it is?
Yeah, depending on in what frequencies are passed by the filter, right? So if I look at a high pass filter here on the bottom, okay, this is saying I basically have 0 magnitude at low frequencies, and I have a magnitude of 1 at high frequencies. That passes the high frequencies. Okay, does that make sense?
So I'm assuming band pass only lets like a certain type of frequency or
Yeah.
range.
Yeah, so band pass only passes a certain range. So in this case, you saw I call these edges omega L and omega H. So it's omega low, omega high. So basically anything between those two things. And a term that you guys have heard many times is the bandwidth, right, of something, right? So the bandwidth is basically what bands pass through that frequency, what band of frequencies passes through. So in the case of that band pass filter, it's basically saying everything between omega L and omega H right there. We use that band pass all the time in radio, right? Let's say, you're trying to listen to a particular radio station, right? So there's a band pass filter that selects just that particular frequency and sends that over to the electronics to amplify it and demodulate it and all that good stuff.
So I have a question regarding the illustration for the low pass filter here. It seems like it goes from 1 to 0 instantaneously, whereas the graph you showed us, there's like a decline and it never really approaches 0.
Yeah, no, you're right. Musa, you are entirely correct. You're very paying good attention there. Yeah, this would be my ideal filter, what we call often the brick wall filter. And that was my next slide here, right? The brick wall filters, meaning it's basically 1 minute it's passing and then boom, it just drops off to 0. That is one of those things that on the 8th day, God said that wasn't happening, right? That doesn't happen, right? So basically for the most part, what you have that happens is you have filters that have a particular roll off. They never ever reach 0, but they tend towards 0. Now, I can make it roll off faster, and I can get it closer to that brick wall, but I can never get it to be the brick wall. I can get it to be faster, but not necessarily instantaneously dropping.
So I would guess to make it faster, that again depends on your values of R and C.
Well, that's a great question. Yeah, no, you're asking all sorts of good questions here. Yeah, so that's sort of right. All right. And you anticipated my next slide, which is if I wanted to make it fall off faster, what I might do is both of these circuits that I put here are low pass filters. The one on the left and the one on the right. Okay. What I see is that the one on the right rolls off faster. Okay.
That's the brick wall.
Well, it's not I'll never have a brick wall, but that looks closer to my brick wall, doesn't it? The one on the right. The reason is because it's second order. If I have a second order circuit, it falls off faster. If I have a third order circuit, it falls off faster still. Fourth order, faster still. Now, if you look at these graphs, particularly that graph on the right, that's a crappy graph.
It filters significantly less frequencies, or significantly more. Very few pass on the one on the right.
Very few pass, but it's also really hard to see it, right? We need a fix for that, and there is a fix for that. All right, we'll talk more about that fix a little bit later, but there is a fix for that. If you guys gave me that graph, you know, I wouldn't give you points for that. It's a bad graph. I can't really tell what's going on there, right? Yeah.
So to like determine which kind of graph it would like which type of frequency it would be, you have to get the time domain and then plug it in random terms?
Well, no, so typically, yeah. So our focus here right now, my focus today was to talk about what is a low pass filter, what is a high pass filter, what are those ideas, and what does it mean? So what it means is if I look at the transfer function, so if your problems are going to be, I'm going to give you a circuit, you're going to figure out the transfer function from the circuit, and then you're going to make plots like this. All right, and we're going to talk more about a specific type of plot that we make. All right, that we do this, but you're going to make a plot, and then we're going to say, okay, well, what happens if I gave you, like in this case, what happens if I gave you an input at a particular frequency? Let's say omega equals 2000, and I said to you, well, tell me what the output's going to be. So let's, to not be too theoretical here, let's look at something like you have on the homework, because I'm thinking more right now about kind of homework for next week. All right, let's say I had that circuit. So the RC circuit that I had there, that RC circuit, let me pull up that slide in particular. All right. So, oops, what am I doing? Okay. All right. Oh boy. All right. All right. So I had this guy right here. So my H of S, this guy is my transfer function right there. All right. And I was told, all right, somebody asked this question. When I'm working in MATLAB, I type clear all. I don't have to, but that makes sure that when I run this program, it's going to zero out everything else that I've done. If I don't do that, then it's possible that some variable that I am about to create and don't put a value for, it may already have a value from something else, and I may screw everything up. So I always initialize everything whenever I write anything. All right. So that's important to usually write, but let's say I had R equals, in my example there, I had 1.59 kilo ohms. All right, so I write 1.59 e to the third, and I write C equals, it was 1 microfarad. Okay. So what I'm going to do is I'm going to say, well, H is equal to 1 over J times omega times R times C plus 1, like that. Now, that's not going to work. I need to give it a particular omega, right? So let's say, I don't know, give me a frequency. So let's say we had omega was 2000, okay? And I run this thing. I'm going to get a complex number for this guy, aren't I? For this H, right? So if I run that, and I look at the result here, it's busy for some reason. There we go. All right, there was my H. Now that's got a real part and imaginary part. That's not useful to me, right? What do I want to know from that? Like the problems I'm asking you in the homework, what am I asking you to figure out for me? I'm asking you for the magnitude and the angle, right? So what would I do? I'd say, well, abs of H is what? Abs of H in this case is 0.3, right? That's the magnitude. And the angle of it is negative 72.5 degrees. So that says right there, if I had an input that was a particular frequency. So too much going on here, right? So what this says, I did it for this particular circuit here. What this says for me is if my input Vn of t was 5 cosine, what frequency did I did 2000 t. This tells me that my V out is 5 times 0.3 times cosine 2000 t negative 72.54 degrees, right? That's basically what it's telling me. And what we often do, and what we're not doing on this homework, just to be clear, homework 8, which is due Friday, you're not making these graphs, right? I'm going to give you in that homework, or I gave you in that homework, all the frequencies, right? So basically what you need to do is you need to basically evaluate the transfer function like this. So everywhere where you see an S equal to j omega, well, everywhere you see an S, you plug in j omega. So you want to talk about what I would do there for you guys? You're going to have some ugly functions probably. You have S, and I would probably say S equals j omega. And then it'll evaluate that. Because you're probably going to have some S squareds and stuff like that. It gives me an easy way to do that. All right, so that's really all you need to know for this homework. The next homework, we get into this idea really hardcore of the filtering and making these plots. All right. But the key takeaway and the thing for us to understand for today is what is a low pass filter? What is a band pass filter? What are those things? All right. So that we can start thinking about it. Now I want to look a little bit at one more thing here today. Come on. There you go. Okay. All right. So what do we use this for? All right. So what we use this for is when we have problems in the real world that we need to deal with, right? So take this example here of, in particular, if I had a circuit, I've given this example before, if I have a solar panel and I have some sort of what I call an inverter, so it's an electronic device that goes from DC to AC. I connect that thing up to the grid, right? So this is Duke Energy over here. And I have an LCL. This is a filter. What order filter is this?
Third order?
Third order. 2 inductors, 1 capacitor. Okay. And what I have is if I look at the current that comes out of this thing, the current, so IL of T, if I look at it, it looks like this. All right. So if I look at that picture right there, I can see that there's 2 things happening, right? There is a 60 hertz component. Right, that's the low frequency here. There's a 60 hertz kind of riding through the middle of this. And added on top of it is a noise that looks like this. So what I did here is I said IL of T is this noise, which is at a high frequency. And I sub L is this guy. The total current is that. Now, if you're Duke and that's your grid, V grid, you don't want that junk. That noise, all of this stuff on top, you don't want this on your grid. So what do we do? We have to filter it, okay? So in this case, what I have is an input signal, I sub L, which has a low frequency term at 60 hertz, and a high frequency term, which in this case happens to be at 10 to the 5th hertz. So 2 pi times 10 to the 5th radians per second, or 100 kilohertz, right? And what I have to do is I have to have a filter that passes the low frequencies and attenuates the high frequencies. So what I'm saying is, what I want is at the frequency of 60 hertz, at a low frequency, I want the magnitude of the transfer function to be 1. And at a high frequency, 100 kilohertz, I want the magnitude of the transfer function to be less than 0.01. Ideally, it would be 0, right? If it was 0, then none of that high frequency signal would make it onto the grid. But like I said, that's not possible. So we say, well, let's make sure that it's less than 1% of what I put in, right? So if it's less than 1%, that means that this guy would be a factor of 100 smaller than it is right now on the screen. That's pretty small, okay? So what I do is I put it through this filter that consists of the 2 inductors and the capacitor. And what happens is the current that goes through there becomes much cleaner, right? What I end up seeing at the output of this filter, I sub G, ends up just being this red line, all right? So that's the whole idea of this kind of filtering, is I have some signals that I want to get rid of and some that I want to pass, right? My goal in this system is to pass power into the grid. That means that I have a voltage source. I need to push current into that voltage source, right? That's how I get power to the grid. But I don't want that noise term to make it to it. So our goal is we need to design a filter to do that. So the thing we got to think through is okay, well, if I have a circuit like that, like in this case, if I have IL and IG, well, what is the transfer function? In this case, my output is IG, my input is IL, and I want to figure out what that transfer function is. And I want to see if that, with these values, matches my goals, okay? So let me just ask you this, how would I solve this in this particular case? If IG is my input and, IL is my input and IG is my output.
So in our filter design, we're basically just playing with the values of the other circuit components to get what we want.
And in this class, you're not really going to be doing design. You're going to be in this, like L2 is 100 microhenries, C is 10 microfarads. You're not ready to start doing design yet. You're more in the mode of, okay, here's a circuit. Tell me what the transfer function is, right? But why do I do this, right? The reason I do this is because for something like this, I want certain things to be made smaller and I want certain other things to make it through.
I'm assuming like how filters work and all that's like signals and systems, right?
Well, it's a circuits 2 thing as well, right?
But
everything we just did is signals and systems, right? I have a signal. That filter is a system, and it consists of circuit elements, and the things that go into it are signals. Right?
But the question in my head is like, so what's actually, because we just say it passes one, but it does the other, but I don't know how it's actually doing that. So it's that question of how the filter passes and not passes the signals and systems.
No.
Class, are we going to discuss that here?
So it's physics why that happens, right? So if why? Because effectively I equals C dV dt. So if I think about why that is, what it's saying is the capacitor, by its very nature of how it opposes the flow of current through it, if I put a high frequency current through a high frequency voltage on a capacitor, I can't get a flow of current at high frequencies. But and the question is, I can't get a flow of current at low frequencies. I can at high frequencies, right? Yeah, that's a physics problem. Signals and systems just has more math to analyze this situation. As engineers, our role is really to really think about, all right, I'm given a signal which looks like this. How do I put together the components of the system to make sure that I get rid of the things I don't want and I keep the things I do?
We care more about behavior, not so much about the why.
We can take that offline. I care about both, I guess, but the real details of why is he opposing the flow of current at high frequencies is a physics problem, right?
So what happens to this filtered energy? Does it get stored? Does it? What happens to it?
Well, basically what it's saying is at a high frequency, in this particular circuit, the impedances at high frequencies are really high, right? So in other words, I can't trigger a flow of current at high frequencies. So if I look at what's happening here, this L2 and this capacitor are in parallel with each other, all right? There's that V grid there, but effectively there's a splitting of currents between these two things, right? Imagine V grid wasn't there for a second, right? So if you think about what's going on and C was in parallel with L2, what's clearly true about this is that some of the current can go through C, some of the current can go through L. At a high frequency, what pathway is most of the current going to go through? Well, I have 1 over j omega C in parallel with j omega L, right? At a high frequency, which pathway is the current going to take?
Capacitor.
So in other words, that high frequency current's going to go this way, and he's never going to make it to the grid. He shunts himself around. At low frequency, he's going to say, boom, boom, and go into the grid. Right, so that's the idea of what's happening, right? It's the physics of the inductor and capacitor means it's effectively trying to, I guess, slosh the energy at high frequencies through part of the loop here, but the low frequency energy is able to make it through to the grid. So the low frequency stuff is basically flowing this way. The high frequency stuff is flowing this way.
Do those currents have the same magnitude?
Those currents depend on whatever the voltages are that are driving it, right? They don't have the same magnitude necessarily.
Okay. Because it kind of seems like if you're talking about the power grid,
you guys are asking some good questions here today. Good questions. Let's take them offline. Key thing I want you guys to understand is the signals and systems part of this, which is to say, all right, I gave you a system, analyze that system. Job of an engineer is usually go beyond the analysis to say, how do I design it? How do I choose the L's and the C's to make that happen? All right, we're not going to worry about that. You guys aren't ready for that. All right. We'll talk more on Friday. We talk a lot more on Friday about how to make these plots. There's a particular type of plot called a Bode plot that we make. We'll talk more about how to make that plot.